Hi everyone. In this last chapter, we're going to study electrochemistry. So I'm going to ask you guys to kind of remember some things that you learned in Gen Chem 1 about oxidation and reduction reactions, or in other words, redox reactions. When we're talking about electrochemistry, we're going to talk about how we can break up these redox reactions and cause them to occur in two different physical locations. And when we do this, we can actually use the redox reaction to produce electricity. So formally, electrochemistry is the study of the interconversion of electrical and chemical energy. Electrochemical reactions will always involve oxidation and reduction reactions. And if you remember, when we learned those in Gen Chem 1, we were always talking about the transfer of electrons. So the movement of electrons is what is going to be the most important thing when we're talking about electrochemistry. There are two main types of electrochemical cells that we will study. One is called a galvanic cell, and galvanic cells are also called voltaic cells, or in other words, batteries, which is the most common name for them. And the other kind that you might not have heard about before are called electrolytic cells. So we'll break up our chapter into talking first about the galvanic cells and then later the electrolytic cells. Before we dive into electrochemistry, let's do a little bit of a review of what you would have previously learned about redox reactions. You might actually remember this experiment or doing this experiment in Gen Chem 1. It's a very, very common general chemistry lab no matter where you took Gen Chem 1. So in this experiment, we would have taken solid zinc and we would have dipped it into an aqueous copper solution where the copper is oxidized to copper 2+. And so this would be our reactants. And then what would have happened in our product side is we would have seen our zinc going into solution and becoming aqueous zinc 2+ ions, and the solid copper plating out on the outside of the zinc. And so this is a redox reaction. One species is being reduced, the other species is being oxidized. And in this case, it's happening in the same container. This reaction is occurring together in the beaker together. So we used something previously called the activity series. You might recall that. And it allowed us to see who was more active or who was more likely to become oxidized versus another element, usually another metal. So in this example, zinc is being oxidized and copper is being reduced. If we were to use that activity series, we would see that zinc was higher up than copper, meaning it wanted to be oxidized more so because it's more active per se. So active is just another word to define oxidized or who wants to be oxidized. And from there, we could write two essentially half reactions. So just for review purposes, the definition of oxidation is loss of electrons. And you can remember that with the acronym LEO. And the definition of reduction is gain of electrons. And you can remember that with GER. So Leo the lion says GER. Oxidation is loss. Reduction is gain. And once you know those definitions and you commit them to memory, it's pretty straightforward to figure out who's being oxidized and who's being reduced in a redox reaction. So in this overall experiment, our oxidation half reaction would be for the zinc. The zinc started out as a solid, which meant it had zero charge there. And it went into solution and became zinc 2+. So for it to become a +2 charge ion, it must have lost 2 electrons. And notice in an oxidation half reaction, the electrons are on the product side. So anytime you see electrons on the product side of a half reaction, that indicates that oxidation occurred. Now, oxidation and reduction always occur together. So let's look at the other half of this, the reduction half reaction for copper. So copper in this case started out as a +2 ion that was in the solution of that copper sulfate. So there were copper 2+ ions swimming around in there, along with sulfate spectator ions. And the copper 2+ ion gained 2 electrons. And when it gained those 2 electrons, it became reduced down to elemental copper. So it went from having a +2 charge to a zero charge. So it gained electrons in order for that charge to go down, which means it was reduced. Anytime you see a reduction half reaction, the electrons will be on the reactant side. So oxidation half reaction, electrons are a product. Reduction half reaction, electrons are a reactant. And so that's kind of a quick review of, what you would have seen back in Gen Chem 1 when you talked about redox reactions. Remembering that oxidation and reduction will always occur together. And in this experiment, they are together in that same beaker, which we're going to break away from that idea when we start looking at electrochemistry, because we want to harness this chemical energy and convert it into electrical energy by separating the reactions. A few more terms that you might have heard when learning about redox reactions in Gen Chem 1 are called oxidizing agents and reducing agents. So the image on the right is just a close-up atom view of what was taking place in that beaker that we looked at on the previous slide. So an oxidizing agent is the species that is actually going to be causing the oxidation. So in other words, it's what gets reduced. In our copper zinc example, copper 2+ got reduced down to elemental copper, so copper is going to be the oxidizing agent. The reducing agent is the species that causes the reduction. So it's going to be the thing that actually gets oxidized. We started with solid zinc. Zinc became oxidized into zinc 2+ ions, and so zinc would be the reducing agent. Zinc caused the copper to be reduced, so that's why zinc is the reducing agent. And the copper 2+ ions caused the zinc to become oxidized, which is why copper 2+ is called the oxidizing agent. If you can remember Leo and Ger, then the agents are just the exact opposite of our traditional oxidation and reduction definitions. So in this example, the reaction was done in that single container. So when the electrons were transferred from copper to zinc in that redox reaction, the heat generated from that reaction would just be lost to the surroundings. It wouldn't be harnessed to be transferred into chemical energy in this example. So we're going to build upon this now when we study electrochemistry. So now let's pretend that we're going to do the exact same copper-zinc redox reaction, but in this scenario, we're going to carry it out in something called an electrochemical cell, and we'll talk about what that is. In this case, some of that chemical energy that's released from that redox reaction will be able to be converted into electrical energy. And we can use that electrical energy and harness it to do work. And my example that I always use is we're going to turn on a light bulb. We're going to use that electrical energy to power a light bulb. If the light bulb's on, our redox reaction is working. And this is what a galvanic cell is used for. So a galvanic cell, the other name for it is a voltaic cell. And this is where we have two half cells, one that's a reduction reaction, the other that's an oxidation reaction, and they're connected by something called a salt bridge. And we're going to draw all this out and kind of look at all the details of a galvanic cell. But a battery is basically what a galvanic cell is. So we are using a spontaneous redox reaction, one that occurs on its own, to produce electricity. So before we dive right in and actually draw a galvanic cell, I want to go through a couple of definitions. There's a lot of terminology involved when talking about galvanic cells, and it's important that you know what some of these words are so you can understand what we're talking about. First of all, the word electrode. The electrode is a conductor which allows the electrical current to enter and leave the cell. They're usually strips of solid metal, and we'll talk about different types of electrodes that are used, which will be composed of different metals. The electrodes are going to be connected to one another by an electrically conducting wire. So we have to essentially complete the circuit, you'll see. And so there's another wire that's used to connect the two electrodes of each of the half cells together. And the last way that we complete the circuit is through something called a salt bridge. And a salt bridge is a tube that has a solution in it, an electrolyte solution, and it's essentially inert. So the ions that are in the salt bridge could change. There's lots of different ones that could be used, but essentially they do not get involved in the redox reaction themselves. They are very important though because they allow us to complete that electrical circuit. So some common electrolytes that you could see that are involved in a salt bridge are potassium chloride, which in solution potassium chloride would break up into potassium ions and chloride anions, or maybe something like sodium sulfate, which would break up into sodium ions and then sulfate polyatomic anions. But no matter what the electrolyte is inside of the salt bridge, those positive and negative charges will be important, but they do not actually take place in the redox reaction. They're not oxidized or reduced. They're just there to help us complete that electrical circuit. Now remember we just talked about electrodes. The electrodes that are in an electrochemical system are always identified by the names cathode and anode. And the names are always going to indicate the changes, the chemical change that is occurring at that electrode. In the anode of a galvanic cell, this is the electrode where oxidation occurs. So anode in a galvanic cell is always where you will find oxidation. This is where electrons will be produced, and it's where the anions will head towards. Remember, anions have a negative sign, so they have a negative charge. And the anode is assigned a sign, and we'll kind of talk about why it has this sign. You can think about like the negative sign on a battery. So the anode has a negative charge overall. So the negative sign is assigned to the anode. The other half is called the cathode. The cathode of a galvanic cell is the electrode where reduction is specifically taking place. So if one side is reduction, that is called the cathode. This is where electrons are being consumed. They're being used up at the reduction side. And cations will migrate towards the cathode of a galvanic cell. Cations have that positive charge. And so the cathode has a positive sign, has a partial positive sign, has a plus charge on its end of the electrode. So that's like thinking of how your battery has a positive sign. So your batteries, you see a positive and a negative sign. So that's essentially telling you what side is the anode and what side is the cathode. But it's important to know that we're talking about galvanic cells right now, specifically. Remember, there were two types of cells that we're going to study in this chapter, galvanic cells and later electrolytic cells. So I'm being very specific right now, and then I'm saying at the anode of a galvanic cell is where oxidation occurs. At the cathode of a galvanic cell is where reduction always occurs. So now let's look at a general schematic of a galvanic cell. And in this example, we have two electrodes. One electrode is zinc, and so there's that solid strip of metal zinc being dipped into a beaker. And then on our other side, our other electrode is copper. So we have this bronzy metal copper solid strip being dipped into the separate beaker. So comparing this to what we talked about earlier when we were just looking at general redox and they were in the same container together, now we have two separate beakers that we're isolating from one another. Our electrodes are dipped into a solution, and our zinc electrode is dipped into a zinc sulfate solution. So what that really means is swimming around in here, we have zinc 2+ ions, and we also have sulfate ions swimming around. And our copper electrode is dipped into a copper sulfate solution. So swimming around in here, we have copper 2+ ions, and we also have sulfate ions swimming around, SO4 2-. The only reason that the color of the solution on the copper sulfate side is blue is because when copper ions are in solution, copper 2+ ions, they produce a blue color. So don't get hung up on that blue coloring of the solution. That's just trying to show you more of an accurate depiction of what the color of that would really be in real life. So now looking at what's going to take place here. On our zinc side, this is going to be our anode, and so that's going to be where oxidation occurs. So you want to remember that anode is associated with oxidation. So we could write that oxidation half reaction. Solid zinc is going to become oxidized to zinc 2 plus, and it's going to lose 2 electrons for that to happen. In order for it to go to 0 charge to plus 2 charge, 2 electrons must have been lost. And notice the electrons are on the product side, which is indicating an oxidation occurring. So really, some of that solid zinc is going away and breaking up into zinc 2 plus ions that will now be swimming around in that solution. On the right-hand side, we have our cathode, which is where reduction will take place. So our copper 2 plus ions that are swimming around in that solution are going to be picking up electrons, specifically picking up 2 electrons, and the copper will plate out on the surface of the electrode as solid elemental copper. And so this represents our reduction reaction for copper 2 plus ions, and notice that the electrons are on the reactant side, which we said was a reduction. So you want to remember anode oxidation, cathode reduction. The sign of the charge that develops at the anode is negative. It gets a slight negative polarity due to those electrons being produced. And the sign on the cathode is a slight positive polarity because that's where reduction takes place and electrons are being consumed. Now, this wire is what's connecting our anode to our cathode. And so whether you see a voltmeter at the top here or you see a light bulb, essentially that's showing you that we're producing electrical energy from our chemical energy. And electrons always flow from the anode to the cathode. So electrons are being produced at the anode because they're a product of that half reaction. And so they're flowing in this direction. They're flowing from here all the way over to here. Where they're being consumed, they're a reactant at the cathode. So it's important to always remember electrons flow from the anode where they're produced to the cathode. And another thing that we have to talk about still is the salt bridge. So we said that was used to help complete the circuit. In this example, potassium chloride is the ion that, or the salt that's going to be in the salt bridge. So it'll really be ions in there. So you can think about that like you have K plus, Cl minus, K plus, Cl minus. You have a bunch of potassium and chloride anions that are packed into that salt bridge, which will help us complete the circuit and connect the two half cells together. So anions will always move towards the anode, and cations will always move towards the cathode. So anion, anode, cation, cathode. So that makes that relatively easy to remember because those match. So how our ions are going to flow then is, for example, our sulfate is an anion, it has a negative charge. Those are going to flow towards our anode. Those are going to start surrounding that zinc electrode. But also chloride anions that are packed in that salt bridge will flow out of the salt bridge and into our beaker and head towards the anode as well. On the other side, our cathode, that's where cations are going to flow towards. So copper 2 plus ions in solution are going to flow towards our solid copper electrode where they're going to get reduced. But also positive potassium ions that are in our salt bridge are going to flow out and also head towards that cathode. So any cations will flow towards the cathode and any anions will flow towards the anode. And this allows everything to remain electrically neutral within the two separate galvanic half cells by having those ions displaced from the salt bridge. So this is a general picture that you're going to want to practice being able to draw and understand for basically any galvanic cell that could be made up with different electrodes that you would be assigned. So it's important to practice drawing it, practice using the terminology, practice remembering the direction of electron flow and how to write oxidation and reduction half reactions. So now let's take a look at what our electrodes would technically look like after this redox reaction has ran for a little while. So let's, set it up, let some time pass. There will actually be a visible change at each electrode. The zinc, which was going to be losing mass because it was going to be oxidized into zinc 2+ ions, will get smaller, it will lose mass. The copper was going to gain mass because that was going to be reduced down to elemental copper from those aqueous copper 2+ ions in solution, will get bigger, it will gain mass. So you can see that visible difference in the electrodes after the reaction is complete, or after it's been allowed to go for some time. There's that visible change.